Hello and good afternoon, everyone. Today, inshallah, we will continue our journey with basis, spans, and vector space. This is the week 9 lecture, and we will go through null, row, column spaces in this lecture. I believe I sent you the slides of this lecture, and you already have it on Moodle. You have videos for this lecture on Moodle, so you shouldn't have any problems whatsoever. I will continue and start this lecture with the orthogonality condition between vectors. If you have two vectors like u and v and they are orthogonal, then the dot product of these two vectors is going to equal to 0. This is really a very simple check in order to know if you have orthogonal vectors or not. So for two vectors u and v belongs to the set of Rn are orthogonal if their dot multiplication is equal to 0. What's the dot multiplication? Is multiplying the corresponding coordinates between these two vectors. If the sum of these two of this multiplication is equal to 0, then those two vectors are orthogonal. So it is a check if these vectors are orthogonal or not. For an example, consider u and v two vectors in R4. So each one of these vectors consists of 4 components. In order to check if they are orthogonal or not, all I have to do is to multiply the corresponding coordinates in these two vectors. So simply, it's gonna be 1 times -2, then plus 2 times 1, 2 times 1, then plus, I would multiply 3 times -4, and then multiply 4 times 3, as you can see, and get the sum of all of this. So very simple. You will discover that the first term is -2, the second is +2, and then this term is gonna equal to -12 plus a 12, when the result is equal to 0, which means that these two vectors are orthogonal. So as you can see, the check is really very simple. All I have to do is to multiply the corresponding components in these two vectors. So multiplying 1 times -2, 2 times 1, 3 times -4, and 4 times 3, and getting the sum of all of this is gonna equal to 0. It's really very simple, straightforward, and this is the way to check if you have two vectors orthogonal or not. Actually, this introduction will help us in the remaining of this chapter and to know about the nullity, about the row space, the column space of matrices, as you will see. This is really a very interesting lecture. Okay, the null row column spaces on continuation. The orthogonal complements of S are the orthogonal set of vectors on the plane S, and they can form a vector subspace of R3. This is really a very good concept. If I have S like the back of my hand, which represent a plane, as you can see, and if I have a vector which is perpendicular on all the vectors on this plane, then I will have a set of sub-vectors or a set of vectors. All of them are parallel to this guy, and they will form a sub-vector spaces orthogonal on this plane. And this statement is deep, actually. So once more, the orthogonal complements, which are the vectors that are orthogonal on the set of vectors in S, are the orthogonal set of vectors on the plane. As you can see, all the vectors who are parallel to this vector is going to be orthogonal on this set of vectors. Okay, every plane of R3 passing through the origin is a subspace of R3, and the complement is also a subspace of 3. The definition, let W be a vector subspace of Rn. The orthogonal complement, we will denote it or symbolize it by W and the perpendicularity sign. So for all the vector space Rn, all the orthogonal complements on W in Rn is going to be Wt. And of course, it will prove or hold the condition that if you have vectors belongs to W and the vectors belongs to the orthogonal complement and you multiply them together, the result will be 0. And this is what's stated here. So if the set of all vectors of Rn which are simultaneously orthogonal to all vectors of W, that is the orthogonal complement or the orthogonal set of vectors that are perpendicular on V such that V times U is equal to 0. And that goes for every U belongs to W. This is how to find the orthogonal complements. So in this part of this chapter, we saw how to, first of all, what's the condition of orthogonality between two vectors, and then we already defined the orthogonal complement of vectors on certain plan or certain set of vectors. Okay, how to get or what is the orthogonal complement of W with a span 1, 2, 3, which is a subset from R3 or a subvector space from R3. In order to do this process is really very simple, but you have to perfect it. The steps are really very simple. All I have to do, or my knowledge at the time being, that the orthogonal complement, it is the set of the vectors of the components x, y, and z. That's the vector, which is perpendicular on the set of vectors 1, 2, 3, which can be simply represented by k, 1, 2, 3. If you do the dot multiplication, the result will equal to 0. Which means that's the set of vectors in WT which is perpendicular on the set of W. That's the condition. Of course, K belongs to R, and this is how to generate all the vectors belongs to W. So if you look closely to this relation, I can divide on K, which is a number. So I will have x plus x plus x times 1, and y times 2, which is 2y, plus z times 3, which is 3z, equal to 0, which is the dot product of two orthogonal vectors. From this relation, this is the relation that will connect the orthogonal complements of on W. So simply from here I can state that x is equal to negative over 2y minus 3z. That's the condition. And so the orthogonal vectors or set of vectors will be those set of vectors in R3, x, y, and z such that x is equal to negative 2y minus 3z. Of course, x, y, and z belongs to A. So if we simply do the substitution, replacing x by the values of negative 2y, negative 3z, I will have negative over 2y minus 3z and y. Okay, just a second, I'm sorry. Okay, just a second. Sorry. Okay. Okay, I'm sorry for this technical issue. It's just the cable, the HDMI cable having some problems. So I have now negative 2y minus 3z and y and z. This vector can be extended into two sets, which is gonna be negative over 2y and y and 0. This is for the first set, and plus the second set, which is negative 3 over z, 0, and z, which can be easily simplified to the w of t is equal to the set of two main vectors. That's the basis, which is negative 2, 1, and 0, and for the other one is negative 3, 0, and 1. And that's the span of the orthogonal subvector space on this subvector space. As you can see, it's really very simple. and it depends only on the multiplication of x, y, and z times 1, 2, 3, which is the span of the vectors that generate W. And so it's really very simple, as you can see. I will go on this once more with you with the slides. And of course you have this PDF, I sent it to you earlier. So to determine the orthogonal complements of W, we already know that any vector of W will be on the form of K1, 2, 3, that's the generating. And in order to have them orthogonal, so the dot multiplication of x, y, and z times K1, 2, 3 is going to equal to 0. So simply dividing on K, you will end up having this equation, which is x, y, z times 1, 2, 3 equal to 0. I will multiply the corresponding coordinates from the two vectors, and this is how I will have x plus 2y plus 3z. Getting x on one side will leave you with the condition that x equal to negative 2y minus 3z as we did. Here we go. Replacing x by negative 2y minus 3z, then separating the y and z's together. That's the y part, that's the z part. So I have now the set which is, or the span of this orthogonal complement of W, which is negative 1, negative 2, 1, and 0, and the negative 3, 0, and 1, exactly as we did. So the span of the orthogonal complement is going to be negative 2, 1, and 0, negative 3, 0, and 1. So the procedure in order to find the orthogonal complement of a set of vectors is really very simple. Once more, I will go through this slide once more. But before we complete, remark that the dimension of W of this span is just only one vector, so the dimension is 1. The dimension of the orthogonal complement is 2, because it has two main independent vectors in the span. The sum of them is going to equal to 3, which is the dimension of the plan that you, the subvector space that you are representing. So noting that W is a vector subspace of R3 with dimension 1 and its orthogonal complement with dimension 2. This is shortly the steps directly. So I will have the span, I've multiplied in x, y, z, I've simplified the equation, I had the condition, making the substitution, and simplify stuff till you get the span of the orthogonal complement. It's really very simple. I have now a very good proposition which insists on the fact that the dimension of any set and the dimension of orthogonal complement will equal to n, which is the number of the dimension that already exists in this set as you saw. So once more, as I told you, that's the dimension of W plus the dimension of the orthogonal, which is T. Let's go and do another problem, but in this time, I will talk with the span of two vectors, 1, 2, 3, 4, 5, and 6, and the set that with the span of these two vectors, I need to find the orthogonal complement. And also check the dimension theory, that dimension of W plus the dimension of the orthogonal sets equal to n. Solving such a system or such a problem is really very simple. It's going to be repeating the same steps that we did previously. So simply, all I have to do is to start with, I know that in the orthogonal complement, the x, y, and z, which is the component of the vectors here, it's going to be perpendicular on both of them. And this will give me two equations. The first is multiplying x, y, and z times 1, 2, 3. The second will be exactly the same. X, that's x, y, and z dot this vector, and the both of them is going to be equal to 0. So simply, I will have x, y, and z times the vector 1, 2, 3, which equal to 0, and this will develop an equation. The second equation is going to be x, y, and z, also dot the second vector, which is 4, 5, and 6, and this is how we are going to get the orthogonal complement of this problem. Sorry for this technical problem related to the pressure. Just in a second. Okay. Okay. Okay, just a second. Okay, as I told you, once more, Okay, very good. Now I will have x, y, z times 1, 2, 3, x, y, z times 4, 5, and 6. And this, as I told you, will form another equation. So this is going to equal to 0, which at this time I will have a system of two equations in two unknowns. So simply I will have x plus 2y plus 3z equal to 0. And also I will have 4 of x plus 5 of y plus 6z equal to 0. These are two equations in three unknowns, which is for a homogeneous system, which is really very simple to solve. All I have to do is to solve this system in order to minimize or to get by stuff. So it's a 1, 2, 3, or the conditions for the orthogonal complement. So it's 1, 2, 3, 0. The other is 4, 5, 6, and 0. And I will start with the row operations, trying to reach a reduced echelon form. This is how I'm going to develop the relation connecting these vectors. So simply all I have to do is to get the first row, as you know, 1, 2, 3, and 0, multiplying the negative 4 and adding on the last row. So negative 4 plus 4 is equal to 0. Negative 8 plus 5 is going to equal to negative 3. Negative 12 plus 6 is going to equal to negative 6 and 0. The second step is to simplify or getting the pivot of the last row. So I'm going to divide the negative 3, which will leave me with 0, 1, 2, and 0. Then multiplying by negative 2 the second row and add it on the first row, I would have 1. Then I will have 0. Then multiplying by negative 2, it's going to be negative 4, plus 3, negative 1, and 0. Now I can expand the solution. The solution will be x minus z equal to 0, and y plus 2z equal to 0, which will lead to x is equal to z, and y is equal to negative 2z. Using these conditions, I can find the span of the orthogonal set. So the orthogonal WT is gonna be the set of x, y, and z, where such that x, y, and z belongs to R. And I will replace x with the value z, and replace I will replace x with the value of z, replacing y with negative 2z, and so such that z belongs to R. So simply the span will be 1, negative 2, and 1. It is the set that form the orthogonal complement. If you remark once more the dimension of W in this problem, okay, it was 2. So once more, here's the problem. So the dimension is 2. The dimension of W, so the dimension of W plus the dimension of the orthogonal complement will equal to n. The dimension of W is 2, the dimension of the orthogonal is 1, and the result will be 3. This problem showed you how to get the orthogonal complement if you have the span of two vectors generating this subvector space from R3. Just going through the dot multiplication, equal to 0, a system of equations, simplified, you will get your relation, then you will be able to write WT. I will repeat the whole thing once more using our slides. And this way you will be able to do it. Please try to resolve these problems. It's really very important for you. So now, and once more, I will do it with you. So I need to find the orthogonal complement, as I told you, of W. So remark that the vector of these subvector spaces of R3 with respect to this span is a linear combination of these two vectors. That's the orthogonal complement will be on both of them. So simply multiplying x, y, and z times 1, 2, 3, and the x, y, and z times 4, 5, and 6 will give you those set of equations, 2 equations and 3 unknowns. In an augmented matrix for a homogeneous system, you will have this form. Okay, doing the reduced echelon form, you will be able to get 1, 0, 0, 1, and this is going to be negative 1 and 2, so x minus z equal to 0, and 1 plus 2z is equal to 0. From them, I will get the conditions that x is equal to z and y is equal to negative 2z. So once more, that's the end of the previous slide. Now, for the orthogonal complement, which consists of x, y, and z, which belongs to R3, I will replace x with z, y with negative 2z, and so I will be able to get our span of the orthogonal complement of W. And once more, the dimension will hold, the dimension theory will hold, which is the dimension of W, as you see, it's 1. The dimension of R of the subvector space is 3, minus the dimension of W, which was 2 vectors, and it will, as you can see, it will be satisfied. Or the dimension of WT, the dimension of WT plus the dimension of W equal N, which is the dimension of your vector space. So 3, W is 2, and the orthogonal complement is 1, and it is correct. Those couple of problems is really very important, and you will find more by the end of this lecture. Now I have the orthogonal complement, as you can see, and the proof of the law of the dimension is correct in front of you. Now, this is once more shortly. That's the system of equation, putting them multiplying equal to 0, which is the condition for orthogonality. The set of equations, put them once more into the augmented matrix. Work your magic with the row operations. We have reached the reduced echelon form. So simply x is equal to negative z, put the conditions and the problems in front of you. Now I will go to the theorem. Let W be a vector subspace of Rn, and WT is also a vector subspace of Rn, and the dimensions is equal to n, and we already checked that in the previous 2 examples. Once more, all the resources of this lecture, you will find them on Moodle, and also the recorded lectures are on the YouTube, so you should be in a very good shape. Now I need to talk about a very serious topic and represent a weight in our exams, either in the coming midterm or in the final exam. This needs concentration and needs a good memorization of the laws that will be stated here. It's all logic, very simple, and it's all connected to each other. So all you have to do is to focus as much as possible and try to memorize these laws. I'm going to talk about the null, row, and column spaces of any matrix. So we will start by defining A, which is a matrix, regardless about this matrix. Is it a matrix for a change of basis? Is it a matrix of a linear transform? This matrix, which is A, with m rows and n columns. It's an m rows and n columns. Okay, we found that the null space. What's a null space? The null space of A, and denoted by null of A. This is important, this is serious. I want you to memorize it. This is null of A. And the vector subspace of Rn corresponding to the solution set of a homogeneous system. What's a homogeneous system? The homogeneous system is simply AX is equal to 0. All of this is stated simply here. So once you hear the null of A, it means we are aiming to have a solution for a homogeneous system for AX is equal to 0. And of course, in the subvector space we are in. This is what's called a null of A. The row space of A, and they denoted by row of A, and this is serious, once more, you have to memorize it very well. Row of A, it is the span where the vectors are the rows of this matrix. The vectors are the rows of this matrix. That's the row span of A. And also we define the column span of A, which is defined by column A, that's the column span, and it is the span of vectors where the columns are the vectors of this span. So column A, it's the span C1, C2, Cn, which are the columns of this matrix. I want you to memorize that in the number of the columns in this matrix and in the number of rows. So now, after defining what's the null, okay, which is a solution for the system AX equal to 0, and that will have meanings we will see. The row span, which is simply the span of the set of various rows of matrix A, and the column span, which is also the columns of this matrix. Okay, solving the system, of course, this is rows of A forming the row span, and of course the last one, column of A forms the column span. I want you to memorize this slide really very good. Okay, once more, you will have very important slide, which states that the orthogonal complement, you know how to get an orthogonal complement. You know, if I multiply two vectors, the result will equal to 0. So, the first part of our lecture showed you how to get an orthogonal complement on a certain set. Now, the row of A, the orthogonal set is equal to null of A. So simply let A be an n by n matrix. The orthogonal complement of the row space of A is equal to the null space of A, that's row A orthogonal equal to null A, as you can see. Okay, really very good. And then this is very important, that n with the number of columns of your matrix minus the dimension of the null of A. What's null of A once more? This is the solution of a system of AX equals 0. Yes, you are correct. Equal to the dimension of the rows of A, equal to the dimension of column of A, and it's equal to the rank of A. We will check each part of this statement. This is really serious and important. Okay, I want you to memorize that the orthogonal complement on the rows of A is equal to null of A, and of course, this law is also very important. Okay, we need to check all of this. So let's try this matrix. We need to find the null, row, and the column spaces of A. And this is really very simple. All I have to do is to take this guy, which is A, and insert it in a homogeneous system, which is simply AX is equal to 0. And try to work our row operations in order to find the relations between X and Z, Y and Z, or to see the rank and what's gonna be. So simply, I have this system, which is really very simple. 1 triple zeros, we are talking a vector in R4, and then you have 1, 2, 1, 0, and then 1, 4, 2, and 0. So all I have to do is to work your magic with the row operations. So simply, I can divide the second row on 2. So the second row simply will be 0, 1, and 2. Then I will multiply the pivot of the second row in -1 and add it on the third row, which will give you 0, 0, 0, and the last row is 0 also. Okay, multiplying the second row by -1 and add it on the first row in order to get this element is 0. I'm trying to reach a reduced echelon form in this situation. So it's going to be 1, 0, multiplied by -2, by -1. -1 plus 1 is equal to 0. -2 plus 1 is going to equal to -1. So instead of working with the rank of this matrix is equal to 3, I ended up working with this matrix with the rank is equal to 2. So if you look closely, you will have 4 times 3 matrix, and the rank of A at the time being is 2. So that means the null, okay, the null set of A with dimension is gonna be equal to 2. That's the dimension of the null space of A. And also, based on this solution, I now know that x1, for example, minus x3 is equal to 0, and x2 plus 2 of an x3 is equal to 0, and this will lead to x1 is equal to x3, and x2 is equal to negative 2 of an x3. So if I'm talking about the set of vectors that I'm going to deal with, I have a relation connecting them. Not just only of that, but also I have the row span. I can get the row span of this matrix, which is gonna be the span of these two vectors, because these two matrices are equivalent to each other, which is 1, 0, and the negative 1, and the second row is gonna be 0, 1, and 2, and that's the row span of this matrix of A. If I want to get the columns of A span also, I can, because once more, I will see the independent set from this reduced echelon form. The pivot of the first vector is already exist, which means my first vector is with me, y triple zeros, and the vector, the pivot of the second column, which represents the second vector, is also exist. So it's going to be 1, 2, 1, and 0, and that's the row space, that's the column space, and the null space already, we know the dimension of it. Once more, I will repeat all of this with you on the slides. So it's really very simple to get the null space, the row space, the dimension of the column space and its dimension, and I will check everything with you once more. So once more, null space of A is denoted by A of x, and I'm going to solve the system. That's the matrix. I will start with the row operation. As we saw previously, I ended up having this reduced form, which means the rank is equal to 2, and the relation is x1 is equal to x3 from the first row, and from the second row x2 is equal to negative 2 x3. Okay, from all of this, the null space is x1, x2, x3. I can make the substitution. So the null space is gonna be 1, negative 2, and 1, with a dimension equal to 1. That's the null space. Okay, for the row space, I ended up having these two rows, which are the vectors controlling the span. I started with the 3 rows, okay, but those 3 rows, it contains one of the rows which is dependent on the other. So a simplification is required, and it's gonna give you the first row and the second row. If I want to get the span of the columns, okay, or the column, the span of the column of A, it's really very simple to get the span of this subvector space. I will look to the pivot in the first row, which represent the first column, and the pivot of the second row already exists. So I'm going to take the first 2 columns, and those will represent the vectors of the span of the column span. If I want to check the relation of n minus dim equal to dimension of row of A equal to, it will be checked easily. So let's start doing this check. The number of columns here, it's 4 rows with 3 columns. So it is 3 minus. According to the null space, I have just only one vector as a span. So it's number 1. And it's going to be equal to 2. The dimension of the row span consists of 2 vectors. So it is already 2, which is correct. The dimension of the column also, it consists of 2 vectors. So it's also 2. And the rank is 2 rows so it's gonna equal to 2 also in the reduced echelon form. Now you can see that the null space, the row space, and the column space, all of them adjusted really very well, and that's the differences or statement of the dimension, either for the dimension space of the rows, dimension space of columns, or the rank, or the difference between the number of columns and the dimension of the null space. Of course, this is to represent that 3 is the number of columns, if you forget. This is once more, so quickly, null means the solution system or a solution of a system of equations. I've already sent you this slide. Get the row space of A, reduce it depending on the echelon form of A, same for columns. And once you start working with it, I will end up having this relation. Once more, the null space will give you this vector, and this is the row and the column space. Here, look to the pivot of the reduced echelon form, and they take the row vectors from A, as you saw. And in a similar manner, you can get also a row span containing these 2 vectors, and in a similar manner, getting the column span according to the vectors, exactly like the previous slide. Those are the vectors that we are talking about, which are relative to the pivots of the reduced echelon form, which is 1, 0, 0, and 1, 2, 1, and 0. You will find them here. So this problem is really very nice, and you have those slides with you. Now, let A be an M by N matrix, and be a matrix in the echelon form, row equivalent to A, then the non-null rows of B as vectors of Rn forms the basis of the row. The columns of A as vectors of Rm corresponding to the columns of B with pivot form a basis of the columns of A. This summarizes the steps that we saw previously. That's another example for a matrix which is 3 rows, 4 columns, and we need to find its column, the basis for the null row and the column spaces. Also, with the same steps, try to reduce to the reduced echelon form. So I will have to multiply the second row in a -1 and add it on the first row. Simply, I will have this guy. So the rank is 2. Remember, the rank of the null space is